right, welcome back again. This is lecture 6 for light, chapter 7. This is where we left off talking about why things look different when you're inside or outside. Next thing to look at is selective transmission. It's a lot like selective reflection, which is what we were just talking about. The difference is, obviously, this is transmission, so the light traveling through the objects, specifically transparent objects. And so with selective transmission, the object is going to appear to be the color that the light is being transmitted through it. So the most common example of this is stained glass. And so you've got, again, the different light frequencies, red through violet, and the glass is going to appear the color of the frequency that is transmitted through it. All of the other ones are going to be blocked, and so this is blue glass, and it's going to appear blue because that's the frequency that's allowed to pass through it. So up here you've got ones that are allowing red frequencies, orange frequencies, and so on. So very much like selective reflection, just we're looking at transmission now, allowing that frequency through the object rather than bouncing it off. All right, now we're still looking at color. So I told you we could look at pigments because we've been looking at how the light frequencies interact. So now we're going to see how we actually make color on something like paper. So what happens if you mix red, green, and blue paint? Well, if you've ever done this before, and I'm sure you have, or been around a kid recently who has, when you mix red, green, and blue paint, you get this weird, like, brown color, right? So, pigments, which are what are in paints, are particles that are going to absorb specific colors or specific wavelengths of light. And then, again, reflect any of the other ones. So, the pigments are going to actually appear to be the colors that they don't absorb, that they reflect. And so if you've ever gotten a color printer, you know that these are the inks that you're using. They're marked as cyan, magenta, yellow, and then black. And if you've ever wondered why they're cyan, magenta, and yellow, it's because they're going to be used as what we call subtractive colors. So we saw this color wheel before. This is the additive colors for light. So we take the green, red, blue, put those together, we get our white light, and so on. Well, with pigments, we can take yellow, cyan, and magenta and use their absorption properties, mixing them together to make the primary colors. So we can take cyan and magenta. When we mix those together, they're going to make blue because those two pigments interacting with each other are actually going to interact with the light that's hitting them and reflect blue back to us. So let's take a look at what this looks like, for example, when we make a picture. So here is the same picture, and this picture is printed 6 times. So the top ones is pretty easy to see how they've done these. These are the magenta, yellow, and cyan. So this picture, picture D, are these 3 overlaid on top of each other. So you've got the 3 colors laid on top of each other. And you can see that once you do that, you start to get all of the different colors that we recognize. But it still looks a little weird, and that's because the black is missing. And so that's what E is. E is that black. Once you overlay the black, then you get the sharpness of the image that we're used to seeing in a photograph. So let's see how these pigments, the magenta, yellow, and cyan, work. So let's focus in the picture down here on one of the balloons. So let's say, for example, blue. So if you look up in these pictures up here, if you notice, we've got no blue in the yellow. We do have we've got color here on the cyan, and we've got color here on the magenta. So if we add the magenta and the cyan together, we're going to get a blue color, and we don't want any color in the yellow because that would actually combine together to make white light. I don't know if you remember, but if we get that yellow combined together once we make blue, we're actually going to cancel it out and it would make the balloon white. Okay. And so you can do the same thing. You can take a look at the red balloon. We've got the red balloon here in the picture. We've got the red balloon here in the picture. So we're adding the yellow and the magenta together to make that red color. We don't have it in the cyan because, again, that would cancel it out. So you can do that for balloon after balloon. We've got no balloon for the green here in the magenta, but we do have it in the yellow in the cyan. Those two are going to mix together to make the green. If we had the magenta, it would cancel it out. And so this is how these guys work. They're going to add together to make those pigments, but they're actually working to subtract out the frequencies to make our picture. All right, so this last section is kind of just some random properties of light, but they're properties that you're familiar with. So the next one is dispersion. Dispersion is the property of any transparent material where the index of refraction varies with the wavelengths. So here we're talking about where the index of refraction is not the same for the Roy-G-Bv. So index of refraction changes for red or yellow or green or so on. And so since the index of refraction is different for each wavelength, when the light actually moves into this transparent material, the light starts to spread apart. Okay? And what happens is you get violet refracting the most. Now in this picture we only see blue. Violet would be just below this. So the white light comes in, the light starts to refract, and normally in most transparent materials they would all refract the same. But here, because of the material, they all start to refract at slightly different angles. And so the light spreads out so that when they leave the material, they refract again and spread out even more. And so you get these large bends, especially when you get to things like the blue and the violet. And then you can see that red refracts the least, very little bend for the red. So what do you know this from? Well, the best example of this kind of dispersion is a rainbow. So rainbows, these guys happen because of this refraction property of dispersion. So sunlight is going to enter into our raindrop over here. It's going to refract because it's entering from air to water. So the frequencies are going to spread out. Then it's going to reflect off the backside of the raindrop. It's not going to exit. Then as it leaves, it refracts again. The raindrops work basically as a little prism. And when it gets to that second refraction, it spreads out into what we see as a rainbow. All right. Now, the thing is in order for us to see a rainbow, the sun has to be behind you. And this is because of how this works. You can see the sun's coming in and then refracting, reflecting, refracting, and then the light comes back to you. If the sun is in front of you, then the rainbow would be actually projecting the other direction. So this is why you can only see rainbows if the sun is behind you. Each of the drops is actually dispersing a full rainbow, but as you can see up in this diagram, only one of the wavelengths from each raindrop is actually going to hit your eye. So one is going to give you red, one's going to give you orange, and so on to build the entire rainbow for you. So it actually takes lots of water drops in order to build the rainbow that you see. And this is why the rainbow moves when you move, because each of those raindrops is creating that little mini rainbow for you. So as you move, you're moving and you've got new raindrops that are reflecting those new wavelengths right to you. Double rainbows, if you've ever been lucky enough to see a double rainbow, this is actually caused by extra reflections in the raindrops. This is not common, but it does happen. And the double rainbow, if you can see it over here, they're always going to be dimmer because the extra reflection loses energy, and they're going to be reversed in color. So here's the normal rainbow, right? Red, orange, yellow, green, blue, violet. Here's the double rainbow. Red on this side, orange, yellow, green, blue, violet out here. And that's because of that extra reflection. It flips the rainbow around. So it changes the direction. So can you ever find the end of the rainbow, right? Because everybody wants to know, can we find the end of the rainbow? Can we find the, that mythical pot of gold? The answer is unfortunately no. And this is because of that property of reflection and refraction with the raindrops. What's actually happening, you just can't see it, is you're actually making a ring. So the refraction and reflection is actually making a full ring. It just looks like a bow because it gets caught off by the ground. If you actually see a rainbow from an airplane, it actually does look like a ring, which is kind of cool. It's not common, but you every once in a while can see one of these